This is problem 89 of Neetcode 150, graph valid tree. So we're going to be given n, which is going to represent the number of nodes, and they're going to be labeled from 0 to n minus 1. Okay? So if we are given 4 nodes, we are going to have the nodes label 0, 1, 2, 3. We are sure that we are not going to receive something like 13, 14, 15, and 16. Great. So we're going to also receive a list of undirected edges. So each edge is a pair of nodes. And we have to check if what we are given forms a valid tree. So for example, here, if we take a look at the edges, we have 0 connected to 1, 0 connected to 2, 0 connected to 3, 1 connected to 4. And this looks exactly like this. All right. So, what is a valid tree? Well, basically, a valid tree, well, you can simply say it looks like what's on the board right now, right? So you have one node connected to its children. Each children is not connected to another children, right? So if we have one connected to 2, well, we know it is not valid. All right, so this is something we're going to have to take into account. Another thing we have to consider is that we are not guaranteed that we are not going to receive like a 5 here that is totally unconnected to anything else. Right? So if this ever happens, we are going to have to flag this. Great. Another thing that is good to take into account is that take a look at how many nodes we have, right? We have 5 nodes. And how many edges? Well, we have one edge here, another one here, another one here, another one here. That's 4. And this is actually a general rule. So to be a valid tree, the number of nodes minus 1 is equal to the number of edges. So I have 4 edges, and the number of nodes minus 1, which is 4, well, these two equals. Okay? So what I will do is that I will call a def first search function, and on each call I will send the parent, and I will also have a scene set. So if we have something that looks like this, okay, 1 and 2 are connected, I will first start my call at 0, and I will go see its first child here, so I'll go see 1, and then after I see 1, well, or the first search is made in a way that it's also gonna go see its children, so it's gonna go see 4, and after this we are gonna hit 2 non-values, right? The 2 childs of 4 are none because it is not connected to anything else. So what we're gonna do is that we're gonna go back to 1, which is its parent. So this is why in our def first search function we have to pass the parent, because if we ever happen to pass or to see the parent, well, we want to continue the function. We don't want to recall again this def first search, so we go on 4 and then 4 go back on 1, which goes back on, right? This is like a to avoid things that we won't do. Right, so after 1, well, we are gonna technically go to 0, and at 0, well, we're gonna go to 2, and we're gonna notice that we found 1, which is already seen. So in this case, we are gonna return false because this is not a valid tree. So that's pretty much the entire logic. I think that with this in our mind, we can start coding. So first thing, if you remember, the number of nodes minus 1 has to equal the number of edges. So we're going to check that at first. We're going to check if the length of the edges, so whatever its value is, we know if it is not equal to n minus 1, oh, something's wrong. So we're gonna return false right away. No need to pass it through the entire algorithm. All right, and now basically the way to keep track of all the children's and all the related nodes of a particular node is to basically you have two choices. You can create a hash map, but in my version I will create something even simpler because we know that the nodes are level from 0 to n minus 1, so we can use this to basically use the index as or reference to particular nodes. So if I create a graph, okay, I don't even need to create a key or values. I can just say this like that. So give me an empty list, basically for every single node in the range of n, which is the number of nodes that we are gonna have. Right, so we know that when we are gonna say graph at the index 0 because we want the node 0, we are gonna have all the childs or all the linked nodes to that node at the index 0. So knowing this, we can go for all the nodes inside edges. So let me say for A and B in edges. All right. So what we're gonna do, well, we know that they are both related to one another. So inside the index A, I want to append B, and inside the index B, I want to append A. So I will say graph A, that append, and I want to append B, and same thing here for B. So graph B, that append A, just like this. All right, so now we have basically the similar of a hash map, and we know all the related nodes, all their childs, and now we can create this set that we're gonna call scene. So we know that if we ever happens to encounter a node that is in the set scene, we have a cycle, and if we have a cycle, we don't have a valid tree. So that's the very first thing we're gonna call. We're gonna check in our def search function, which I will call is cycle or is cyclic. And inside is cyclic, I want to first check if the node that we are looking at has already been seen. So if it has been seen before, it means that we have a cycle, which is not a valid tree. So if node isn't seen, we are going to return false. If it is not in scene, well, it means that it is a new one, and we just saw it, so we're going to add in scene. Great, and now what we're going to do is that we're going to go for every single neighbors or every single child inside the specific index in graph that represents this node. So I'll say for nay in graph at the index of the node. And now it is possible that well, the neighbor first might be the parent. So if it is the parent, well, we just want to continue. We don't want to call this depth first search on this parent. Otherwise, we're going to do an infinite loop. So if nay is equal to parent, we continue. So we don't want to call this depth first search function. And now we want to call the depth first search function with the neighbor, and the parent of this neighbor will be this node itself that we are at, okay? And if this returns a false, meaning that at some point we have a cycle along this path, well, we want to return false too. So what I will say is that I will say if not is cyclic, within which I will add the neighbor and the node. So in this case, I will return false. All right. So if we actually go through every single neighbor for that particular node and never return false, it must mean that this is a valid path. So we're going to return true. And that is everything we need for our depth first search function. We can actually start calling it starting at the index 0. And if we receive a false, we are going to also return false. So let me actually call my depth first search function within this if statement. So I will say that if the is cyclic, and I want to make sure that the node is going to be 0, so the first node. And first node has no parents, so I will just say -1, can be -10,000 if you want to. Doesn't really matter, as long as it is not a value that is given inside the edges. So if this is not true, we're going to return false. And after this, well, if for example we saw, let me take this again, okay? So if we saw a number of nodes that is not equal to n, it means that we have a problem. And let me picture this really clearly. So if let's say that we have another 5 here, so we're given 6 nodes. All right, so the value of n that we're initially given is 6. So we're going to start our depth first search column 0. We're going to go C1, we're going to go C4. We're going to jump back to 1, but it's parents. So in our code, we're going to say continue. So we're going to go back to 0. And at 0, we're going to go see the next neighbor. So we're going to go see 2. And at 2, well, there is nowhere else to go. So we're just going to go back to 0. And at 0, we're going to go see 3. And at this point, we actually went through all the edges. So we are going to return the entire function. The thing is over. But notice that in scene, we'll have included 4. We'll have including 1, 2. We'll have included 0 and 3. This makes a grand total of 5. But the node, like the value n here, is 6. So we don't have a valid graph if this is not the same, right? So basically, the length of scene has to be equal to n. So at the end, I will simply return length of scene equals n. And that's the condition for our tree to be a valid one. All right, so let's go through the code one more time. Initially, we're checking the number of edges, and we know that the number of nodes -1 gotta be equal to the number of edges to be a valid tree. So if this is not equal, we're gonna return false right away. Then we're gonna create a pseudo hash map, which is basically just a list, list embedded in lists. And each list index represents one of the nodes that we're going to be given, because we know that they are labeled from 0 to n-1. So this is why we can allow ourselves this luxury. And then we're going to go for every single edges, and for every single edge, we are going to append at its index all its neighbors. So we're going to append to the index of A, whatever A value is. We're going to append B because it is in its list. So just so, as we can see to the left, the first edge we're going to get, so A and B will be respectively 0 and 1. So in the graph at the index 0, we're going to append 1, and in the graph at the index 1, we're going to append 0. Then we're going to create our set called scene. And after this is our depth first search function, in which we pass the current node we are at and the parents it is coming from. And if the node is in scene, it means that we have a cycle, so return false. If it is not seen, that is good. We keep going and we add it to seen. And now we're going to go for all the neighbor. So we're going to go again here in our graph, and inside the index of that particular node, we're going to go see all the values in it. And all the values will represent all its neighbors, or all the other graphs, or all the other nodes it is attached to. And for all the other nodes it is attached to, well, we know that one of these nodes will obviously be the parent itself. So if we have the parent, we want to continue. Otherwise, we want to call the def search call on this neighbor, and we want to ensure that we set the parents to be equal to the current node. And if this ever happens to return false, it must means that we blocked here. So here we saw node already, it wasn't seen, so we return false. If we never return false, it must mean that it is valid, so we're going to return true. So then we call our cyclic function, or def search call, at the index 0, so starting at the very first node, and the parent of the very first node does not exist, so we put this dummy value -1, but you can very well put any other values. And then you return false if this statement itself, so this initial def search call, ever return false. Then you want to ensure that we saw the same amount of nodes that we are given. Otherwise, one of the nodes is isolated and it is not a valid tree. Let's test this out. Hopefully it will work. And there you go. I hope you learned from this video, and I hope to see you in the next one.